checking on my phone, and yeah, we're live. But now I'll put my phone down and pay attention. All right. Welcome, everyone, to Bitcoin for Developers 1, Unit 2. Here, again, I'm going over this sort of bonus session, going over this material, assuming that everyone here is already pretty familiar with the material or has gone through Unit 2. So what we're doing here is just kind of, got some nice pictures to get some visualizations for some of the content, and we'll walk through the exercise. And today is really a great chance to ask lots and lots of questions. So as we go through this, we will pause regularly to answer your questions. So as you have those questions, please type them in the chat there, and Mike will help facilitate sending those questions along to me. All right. Unit 2 topic. So this topic is really all about how Bitcoin uses cryptography. So we're going to talk about, what cryptography is. We're going to talk about keys. We're going to talk about the basics of hashing, keys and transaction signatures, and keys and Bitcoin addresses. And again, this is kind of, review of what was in Unit 2. So we're going to go over some of these things just very briefly, and then we're going to get to dive into an example, an exercise where we'll get to actually play with public and private keys using Python. So hopefully that will be fun and helps us get familiar with how to use, cryptography, key pairs, etc. All right, so we will go ahead and get into it. Again, after each sort of segment here, I'll pause regularly to answer questions. So please do type the questions as they come up. All right, so what we're focusing on today is how Bitcoin uses cryptography, because of course, Bitcoin, we call it a cryptocurrency, right? And Bitcoin, spawned the whole crypto industry, right? And of course, this crypto and cryptocurrency all comes from cryptography, right? Because these systems in Bitcoin are, make heavy use of this technology, right? It's a necessary component for Bitcoin. So we're going to dive into that today, just starting at the top. What is cryptography and the different types of cryptographic functions that Bitcoin uses and how it uses them. All right, so Bitcoin uses many cryptographic functions, right? There's a heavy reliance on asymmetric cryptography. So we'll cover that briefly, talk about public and private key pairs. It's also what we'll use in our exercise today. So Bitcoin uses this for signatures, right, to sign data, specifically, the locking and unlocking scripts that you need to transfer funds on the Bitcoin blockchain. We won't get too much into scripting today. That's Unit 7. All right, Bitcoin addresses. We'll talk briefly about how some Bitcoin addresses are derived from public and private key pairs, specifically from public keys. They're derived from public keys, a lot of addresses. All right, we'll talk about hashing, because Bitcoin uses hashing constantly, all over the place, hashes everywhere. It uses them in mining, sometimes in signing, because sometimes you'll hash data before you sign it. It uses them for creating addresses, et cetera, et cetera, et cetera. It uses many different types of hashes. Well, primarily SHA-256, but different types as well, but it uses them all over the place. All right, and what's really interesting here is that I think this is a common misconception, which is very understandable due to the name, right? So Bitcoin is a cryptocurrency, and when we think of cryptography, we think of encrypting data, right? Which is obscuring data using some key or some algorithm to obscure it so it looks like nonsense, but actually you can then decrypt it and get in a useful message out of that. But what's interesting is that while Bitcoin is very reliant on cryptography and different cryptographic functions, it does not encrypt any data. There is no encrypted data in the Bitcoin system. Now, you could somehow encrypt some data and hash it and embed it in the blockchain in some capacity, but the Bitcoin protocol does not rely on encrypting any data. So a common misconception, so let's make sure we understand that. We use all kinds of cryptographic functions for signing and hashing, etc., but no data is actually encrypted. Mike, could you hear the my computer loudly telling me that I just got an email? Should I mute that, or is it okay? Okay. Okay, excellent. Well, apparently I just got an email. All right. So we're going to talk about this briefly. Then we're going to go through, encrypting, signing, and hashing, and then we'll come back to this again. So this is one of my favorite graphics for explaining all of this, right? This showing the difference between encrypting data, signing it, and hashing it. So if we look at this first one, this is the sentence, the quick brown fox jumps over the lazy dog. I think that's just the sentence you always use to show fonts, right? Because it has like every letter in the alphabet. But so we just, let's say this is our message, right? This is the data we have, and then we're going to encrypt it, or we're going to sign it, or we're going to hash it. Now, when you encrypt a message, right, you get, something like this out at the other end, right? This is just example text. This isn't actual encrypted data here, but it looks like this. It just looks like nonsense, like scrambled data. Like that's not English, right? It doesn't look like any language I'm familiar with. It just looks like nonsense, right? Because we have obscured that data, we've encrypted it. And if we did actually take this information here and run it through an encryption algorithm and got encrypted data out at the other end, then there would be a mechanism to decrypt that data and turn it back into this, human readable message over here. But it's just showing what this looks like. You take this data, when you encrypt it, you turn it into something that looks like nonsense, right? It's not human readable. It's not even computer readable unless you have that decryption key. All right, now in contrast, let's look at what happens when we sign something. Here we have our message, and we put it through a signing algorithm. And now often things are hashed before they're signed, but that's not what we're showing here. We're just showing simply this message with a signature. And what happens there is you take the message and then you create a digital signature from that message using a private key, right? And then you get this signature here. So we'll talk about that a little bit more in depth. And then I believe next week we actually get to go into signing and verifying signatures, which will be fun. But this is a bit what this looks like. You take this message and you just add to it, then you add this signature that goes along with that message. And that's a bit what signing looks like. Then we'll take hashing. Again, we have the exact same message. This time we run it through a hash function, and out the other end, we get something that might look a bit like this. Now, SHA-256 is, the hashing algorithm that's used quite a lot in Bitcoin, and there the, digest, like what you get out of that hash is going to be a bit longer than this, but this is a good example. So if you get this just unique identifier of this data, right? So you can see these are all different cryptographic functions which do very different things for us, whether it's obscure the data, add a signature to it for verification, or just give us, this digest or this identifier for that data. So here's this graphic here, and we're going to walk through some of this stuff, and then we'll come back to this when we're done. All right, elliptic curve cryptography. Very cool stuff. We won't dive into it here in depth because we already covered this in Unit 2. And, you don't, like, if you want to work with Bitcoin technology, if you want to integrate it in different places and use it, like, you don't need to be a cryptographer. The level, sort of the depth that it's covered in Unit 2, where we read, I think, a chapter of Mastering Bitcoin. And it talks really about how these signatures are created, these trapdoor functions, this curve, cool stuff. That's really like the level of knowledge that you're going to need to work with this technology, right? If you read that portion and you understood it, and here, you can see it's a very lovely curve, this elliptic curve cryptography. But if you're working with this tech, then that's sort of the level that you'll need. If you want to become a cryptographer, that's a, whole nother field of study, then you really want to understand in depth the math behind this stuff. Or maybe even if you wanted to get into Bitcoin protocol development, then you'd want to. Otherwise, for us, what we read in Unit 2 is going to be pretty sufficient to really, for us to understand how to work with this technology. You really need to get public, private keys, the difference there, how they're derived, why one can't be turned back into the other, etc. But once you got that, you're pretty good to move on and start, playing with the software in other ways. All right, so briefly we'll talk about the difference between symmetric and asymmetric encryption. All right, so with symmetric encryption, you have, let's say, a key, right? Or a particular encryption, sometimes it's like, say, an algorithm, right? But think about it as having one key. And this key or this method of encryption obviously is generally something that's pretty mathematically, sophisticated, right? Very, very cool, interesting encryption algorithms sort of stuff. But here we'll go with a very, very, very simple example to explain the difference between symmetric and asymmetric encryption. And so we'll say our encryption algorithm here is just to take a message, and for each letter in that, the message is, a string in English, and for each letter in that string, we're just going to take that letter of the alphabet and move it over to, right? So then hello becomes this gobbledygook, right? This JGNNQ, right? Which is not easily human readable, right? And this is a very, very simple example, but okay, this could work. So if we have Alice and we have Bob, and Alice wants to send an encrypted message to Bob, just wants to tell him hello, she can use this encryption key here to encrypt this data and send it to Bob. But then the problem is, all right, so Bob would be able to decrypt this message if he knows what the key is, if he knows that we're just moving, 2 letters over in the alphabet. But the problem is, how do you share that secret key? Now, if Alice and Bob are middle school students and are sitting next to each other in class, they can just like whisper it, and they've shared the key. They know their secret between each other. They can then send each other encrypted messages, right? But if you're on the internet and Bob's on the other side of the world, how is Alice going to deliver him, this key, this method for encrypting without other people seeing it and then being able to decrypt that data themselves, right? So this is a problem. And lots of very clever math later, we get asymmetric encryption where you have key pairs. And this is really the magic here. This is cool stuff. So you have public and private keys. And a public key can be used to encrypt a message. So again, if we have Alice and Bob, Alice has a private key, she has a public key. Bob has a private key, he has a public key. When Alice wants to send the message hello to Bob, but he's on the other side of the world, what they first do is just share public keys with each other. Out in the open, out in the clear, they can post it to Twitter, right? Alice can say, hey, Bob, here's my pub key. And Bob can say, hey, Alice, here's my pub key. Now, they might not want to do that. They might want to keep some, they might not want to put that out in the open for other reasons, but you could, right? So someone could intercept that. But what Alice can do is take Bob's pub key and encrypt a message using Bob's pub key, send it through to him, and then only Bob, because we're assuming he's the only person that has that private key, only Bob can then decrypt and read that message, and vice versa. Bob can then respond with, how's your day going, and encrypt it using that Alice's public key and send that out on the clear, on the internet. Someone could look at it and be like, that's gibberish, I don't understand it. Once it reaches Alice, she can use her private key associated with that public key that Bob used to encrypt that message, and she can decrypt it, right? So this is really, really important because it solves this problem of how you transmit this key, the secret key, to decrypt a message. And well, this gets used in many different ways. This is a really good example to keep in your head to just understand why this is so useful and the different components in this. It's key pairs, public and private keys. All right, yep, we've covered that. All right, so that was symmetric versus asymmetric cryptography very quickly. Let's just talk about signing messages, and then we'll pause for questions. All right, so cryptographically signed messages. All right, so signatures provide strong assurance that a signed message is authentic and has not been tampered with. This is really, really important for a lot of different types of Bitcoin transactions, right? I can say, okay, the blockchain says that I have, 5 Bitcoin at this particular address, right? And if I want to send a transaction out on the blockchain that says I'm taking one of my Bitcoins and I'm sending it to Charlie, right? And well, there has to be some sort of mechanism for knowing that it's actually me that's the owner of that Bitcoin that does indeed intend to send it to Charlie, right? And how you do that, at least in a lot of cases, we'll talk about scripting and different ways of doing things in Unit 7, but in a lot of cases, what you do is you just sign that transaction, right? And with cryptographic keys, you can prove that it did indeed come from the person that's associated with that public key, right? So you know that that message had to come from the private key associated with a specific public key, right? That's the only mathematical way that signature could have been created, at least that we know of, right? And we can also prove that that message that I signed hasn't been altered, right? Charlie can't just change that transaction to all of a sudden I'm sending him 2 Bitcoins instead of 1, right? So we can prove we know like where the message came from and that it hasn't been tampered with. That's really important in this case. All right. Signatures can be used to prove that the message came from someone in control of the private key and the public-private key pair. Yep. And to validate a signature, right? So we can go back to that, think of that graphic where we have the message and then we have the signature on that message. So we'll do this next week with some Python, which should be fun. But what you need is you need that message. You need the public key associated with the private key that signed that message, and you need the signature. That way, if you have the message, you have the signature, and you have the pub key from the person that the message came from, you can use all that data to verify that signature and be pretty well assured that that message has not been tampered with. So that's how Bitcoin uses signing. Again, this is a slightly simplified version, but this is, why it's so important to Bitcoin is in many cases it's used to be sure that the person sending that transaction out is the person that actually owns that Bitcoin, right? And the message has not been tampered with. All right, let's pause here because we went through a lot of stuff pretty quickly. And Mike, do we have any questions? Mike, can you hear me? No. All right, there we go. Okay, cool. Excellent. So we will roll along then. All right, cryptographic signatures in Bitcoin. I should have done this slide before we paused for questions. All right, so cryptographic signatures are used in unlocking scripts. Oh, that's all I had on that slide. Right, and again, we go in depth on Bitcoin scripting in, I believe it's Unit 7. So we'll just note that it's used quite a lot. Cryptographic signatures are used quite a lot there, and then we'll move along. All right, now hashes. Bitcoin just hashes things constantly, right? So it's used in all sorts of different ways. SHA-256 is the hashing algorithm most used in Bitcoin, but there's also like the 161. We're going to see it on a couple of pictures here when we talk about address generation. But let's talk about what a hash is briefly. So a hashing algorithm or function takes data, any amount of data, right, whether it's one letter or like, all of Shakespeare's works, and produces from it a fixed length unique identifier. So here's some qualities or properties of hashing algorithms or hashing methods or functions that we look for that makes it very useful for us, right? Collision resistant. That means if I type up a message, right? If Alice types up a message to Bob, just telling Bob about how her day went, and Bob types up another message back to Alice, telling Alice how his day went. These are two different messages, and they're different content in them, and so you should be able to hash both of them with the same algorithm, but get a different output, sometimes called like digest. You should get a different output from these two hashes from these two pieces of data should be different, right? So with a good hashing algorithm, you should not be able to hash two different messages but get the same output, right? The same digest, the same identification, sort of ID for these pieces of data. They should always be different. So that's important. Also deterministic, meaning if Alice types up this letter to Bob, if she hashes it today, she'll get a specific, output from that, a specific identifier for that data. If she hashes the exact same data tomorrow to resend him that exact same message, she should get exactly the same identifier out that, right? So the same input should produce the same output every time. And fixed length digest. So with a lot of this stuff, the idea is to give away as little information as possible. So you want a hashing algorithm that takes all different types of data, just a little bit of data, very short message, a hello, to like a whole, autobiography of my entire life, right? And all of Alice's life, right? Shoved into text. And then both of those things hashed should produce an output that is of the same length, both unique, collision resistant, deterministic, and of the same length. And when you get that, then it becomes really, really powerful for all different kinds of use cases. All right, and hashing is a one-way function, which is important to note that when you hash something, you don't unhash it, right? It's not like encryption where you can decrypt it. There is no way that we know of currently, right, to reverse engineer a hash, to take a specific hash and then turn it back around and take this just, 256-bit string and then reverse that and turn it into all of Shakespeare's written work, right? Like there's no way to do that. That's not currently feasible. So that's just very important to keep in mind. This is not like encryption. It's one way. There's no undoing it. And here's just a quick example of that. Here we have 3 different messages, right? So first one is just a very short one, Fox, right? And we shove that through a hashing function, and here we get just an example output of a specific length. Now we take a much longer message. The red fox runs across the ice. We shove that through the exact same hashing function. Boom, we get a different identifier, right? But of the same length. Then we take that message and we change just one tiny little thing about it. And it can be as tiny as like changing a period to an exclamation point, right? Exclamation mark. And if you change anything about the message, here we just change it to the red fox walks across the ice. You run it through that hashing function, boom, you get something different, right? Of the same length, the output is of the same length, but it's different. And that's really important to note. So here, this is just hopefully helpful visualization of how this works. All right, how do we
We had a question real quick here on on hashing,
that's a good
which
time
I thought
for
would be a good time. I wanted to wait till we finished the hashing presentation. So the question we have here is, so if my understanding is correctly, the message is combined somehow with the public key, then hashed to produce a signature. Is that the is the combination technique standardized or something? Is the combination of techniques standardized, I believe, is how I should say that.
Okay, you dropped out for a second there, though. Might be my internet connection, but can you walk through that question one more time?
Let me give it to you one more time. That might have been on me as well. Okay. So the question is, the message is combined somehow with the public key and then hashed to produce a signature?
Okay. So how do you use hashing and signing together, right? So there are 2 separate functions. They are sometimes used together. In some situations, you may want to take a message, hash it, run it through a specific hashing functions, then take the output of that message, like the hash digest, then use a private key to produce a signature for that specific message. So then if someone wanted to, then you could send that out to someone, and that would be that what you would send is that hash digest, or maybe you would even send well, depending on your use case, right? But you could send that hash digest, your pub key and the signature, and someone would be able to validate that you did sign that digest. But then you maybe also, they already have the original information that went into creating that hash. And so they would be able to, if they knew what hashing algorithm you used, take that message, like recreate it, take that message, run it through the algorithm, see that that hash matches that message, so we can know that that message wasn't tampered with, then validate the signature on that hash to, again, be sure it wasn't tampered with and it came from who we thought it came from. Let's not get too into specifics there, but there are sometimes, people will do things that way, maybe to save space or for a variety of different reasons, but that is a way in which you would combine both hashing and signing. So that answers the question.
Yeah, so there was a second part of the question, which you might have answered, but I don't know, so I'll just ask anyway. So that's not like what you're talking about there. That's not, a standardized technique.
No, in a lot of places that's used, but so there are libraries and functions and stuff that'll let you do those two things together, but you don't have to, right? And it totally depends on your use case, right? But definitely, I don't even know, it might be libraries and stuff I'm not thinking of a clear example right now, but definitely there can be systems where you would want to use those together and you would, but you don't have to. Right.
Okay. All right. Well, hopefully that answered the question, and I'll let you know if we have any other questions, and feel free to leave them in the chat as we go along. I'll go away.
Cool. All right. Talk to you again in a minute. Okay. So hashing uses. So hashing can be used as unique identifiers for data. They can be used to represent data while obscuring the data itself. So maybe you want to reference some data that some party has, but don't want to, publicly post that specific data. You could post a hash of it. And as far as unique identifiers, a lot of times when we're talking about software, there'll be, a particular build of software that then gets hashed to a unique identifier so that when you're downloading it, you're getting that exact version. And then you might even have a hash of that. Well, then maybe that hash was signed, right? So that it came from the developer you want it to come from and no one had tampered with it in the meantime as you were downloading it. So that's a case where you might have both hashing and signing going together. All right, and then we can detect data tampering, right? Again, if you change even if you change anything about the data going into that hashing function, you're going to get a different result out the other end. So you can't even change like a punctuation mark without that digest, the output of that hashing function being different. So it will help you immediately spot any data tampering. All right, and of course, this is used quite heavily in Bitcoin's proof of work mining, which again, we dive into a bit more in depth later in the course. And Bitcoin addresses. So let's here we go. This is the graphic I was talking about earlier, where we can see how this is used here for generating Bitcoin addresses. Now, there's a number of different types of Bitcoin addresses. This one's a very simple one, pay to public key hash, right? So this is the simplest sort of form of Bitcoin addresses. And what you would do is you'd have a key pair, a public key, and that private key. And what would happen is you would use that private key to create a Bitcoin address. Once Bitcoin gets locked to that address, only the associated private key can create a transaction and produce a valid signature to, then move or sort of unlock and transfer that Bitcoin. So once we generated the private key, right, the Bitcoin software would generate the private key, then we would take that public key, we run it through this double hash. So first SHA-256 and then RIPE-MD 160. And this is used largely here because we get the security of SHA-256, which is a very, heavyweight, algorithm for hashing, very secure. And then you run it through the second one because it sort of creates a shorter digest, shorter output. So it reduces the amount of data which goes on the blockchain to save space, et cetera. So you take this hash and then you encode it with base 58, which is really cool. And we talk about later in the course too. I want to say unit 4, but we talk about that later. And then we add, some checksum, like we add some safety checks into there. Again, we'll talk about that later. And you get this Bitcoin address. So you can see here how you take this pub key, run all this hashing algorithms, then some encoding, and you get this Bitcoin address. This is the check encoding. We'll come back to this one when we cover that later from this base 58. It's cool stuff. All right, so Mike, do we have any more questions on hashing before or any of the stuff we covered? Let's go to this slide here, where again, now we talked about encryption, we talked about signing, we talked about hashing. Let's cover any questions before we then get to go play around with this stuff in Python.
I am not seeing any questions right now in the chat. I'll keep an eye on it. I'll talk a little bit more right now, just in case anyone has any questions and they're going ahead and typing away. But I'm still not seeing any come through, and so I guess we can move on. We can always we can answer questions while we're on the other screen as well.
Okay, cool. All right, so we are going to move along then to our exercise, which is to encrypt and decrypt data. And again, while Bitcoin doesn't actually encrypt any data, going through the process of encrypting and decrypting some data via Python will help us get familiar with the use of public and private key pairs. Right, so it'll be fun. Just it's a good intro to using this tech, and we'll walk through it in Python. This is the example found in Unit 2, and I'll just walk through it here, and we can answer any questions as they come up. All right, so first, we need to note that you need to have Python 3 installed. I'm doing this here on my laptop, which is running Ubuntu, and I've installed Python on it. So I'll walk through that here. But there's also, you can do this online. There's all sorts of websites you can go to run Python in the browser. I was doing this the other day in Replit. And that's, they have Python. So you don't have to do this on your machine. You can do it in a browser at various different websites that'll let you do that as well. All right, so we also need to install this particular library here because we're using some cryptography that isn't just standard to Python, right? So we have to install that, and then we're going to create this file. And I'm going to drop out of this screen share, and I'm going to pull this up. Hopefully you all can see this.
Yep.
Here I have this example. And I have lots of stuff commented out, but we'll go through it step by step. And then I have on my computer here, my terminal window. And you can see here, this is the file that we're working with now, and we're going to actually generate a key pair. We're going to look at how to mess with the how we're storing that, etc. And then we're going to encrypt and decrypt some data. And again, this just helps us get familiar with using public and private key pairs and what they look like and how we can generate them, etc. All right, so let's go ahead and get started. So I'm kind of going to be bouncing back and forth between these three windows here. So the first thing we want to do is import the libraries that we'll need. So again, coming back to this code here, Python, we're going to use from this library, we're going to import these functions here. Right, so this is just Python syntax to say, hey, we want to use all of these things in our script below, right? Now, if we're talking about encrypting and decrypting, the first thing we're going to do here is create a message to encrypt. So there we go. And kept it nice and simple. I love cryptography, right? So we've done that. We've got our libraries we're going to use. We've created this message. But of course, in order to encrypt, we first need to generate a key pair. So let's uncomment this and have a look at it. So here we are generating a private key. And we're using sort of this function here to do it. We're saying, hey, we're going to use this library. We're going to use this generate function.
Sorry to interrupt. Real quick, before we get started, we had a question down in the comments. Is there a place where someone could find these files to follow along?
So they are in, I'm taking these examples from the exercise for Unit 2. So this is all in Unit 2. And if you have...
Should be linked in the description below. And if it's not, I'll make sure I do that right now.
Okay, excellent. Yep. Cool.
That was it. You're good to go.
Cool. All right, where were we? So we're generating a private key. So we're using this library and this function, and then we're telling it a bit of data, telling it like what type of private key we want to generate. And we won't dive too into that here, but it's important to note that there's all different varieties, right? So there's all different kinds of private keys and key pairs you can generate. There's all different sorts of, curves that they're using to generate them. I am not a cryptographer, so I won't attempt to dive into the specifics or the merits of one versus the other, but it's important to know that when you're writing this code and you're generating these keys, you have to select an appropriate key type for what you're looking to do, right? So important to keep that in mind here. I think this is just a pretty standard one we're generating right here. Okay, so we always start with that private key, and that's, to kind of think of it just like sort of a random number, but it has to be a specific format, and there's all sorts of, you can really get into depth with how you truly randomly generate something. That's really interesting topic when it comes to Bitcoin, because if you can figure out how someone's generating private keys, then you could potentially find their private key and steal some of their funds. So that becomes a really important topic of conversation in Bitcoin security. But another really, really important thing to note here, which I should probably put in the slides and continue to put in the slides for the rest of the course. I'm actually going to note that. Hold on. So don't roll your own crypto. Crypto. All right. And this is a saying that's commonly said in the Bitcoin world. And it means that like you got to know your skill set, right? So I'm a developer. I work with Bitcoin, Lightning, all of this stuff. I am not a cryptographer, right? So when I want to go in and make use of this technology, I am never going to be writing, right? My own cryptographic library, right? I am going to go find a really well-tested, open source, very, respected cryptographic library that's appropriate for my use case, and I'm going to use that, because you can get yourself into so much trouble if you try and make your own, right? Or even not even making the cryptographic functions yourself, but maybe just using them in unusual ways. So if you do that, right, if you roll your own crypto, you're quite likely, sometimes people do this to try and increase security, but it's much more likely that you're going to wind up losing your funds just due to error and having not tested well, et cetera. Like, you're more likely to, if you roll your own crypto, you're more likely to have funds lost due to your error than from someone stealing it from you. So please just use, well-respected, well-tested, established, open source libraries for this stuff, and don't make them your own unless you are a cryptographer. Then please do so. But if you're not, don't, right? Don't do it. Okay, so now we have a private key. Now we take this public key, and we take this private key that we've generated here, and then run this function on it to generate our public key. So public keys are always derived from private keys. Again, that's discussed in the book. We won't dive into it here. That's in Unit 2. All right, now we want to print out our keys to be sure that we've generated them properly, right? So we went and generated them, and we want to see that we've generated them properly, right? This is important. We want to make sure we're getting out what we expected. And so for this particular bit of Python, what we're expecting is that this is a crypto public key RSA key. That's the type of key we're using here, right? So, oops, I didn't mean to do that. I meant to hit this. So I'm saving this file, right? I'm coming back here and I'm just going to, there we go. I'm going to run this file and see what kind of output we get. And boom, there we go. I get the output I was expecting. This is the type of key that we have generated. This is the class here for it. So far, so good. Let's roll along unless we have any questions specific to what we're doing here.
Not hearing any questions right now.
Cool. All right, so let's move along to the next one. All right, now we want to convert our keys to strings and save them in .pem files, right? And this can be very important depending on what type of systems you're working with, what you're building. You're going to have some sort of way to not, well, quite often you need to generate these keys and then you need to hold on to them, store them in some fashion. So we should know a little bit about how to not only generate them, but how to put them in files and save them. So here, that's what we're doing. We're creating this new variable here, which is this private PEM. We're taking the private key and we're exporting the key. And these are all, Python functions, which we won't dive in depth on here. I don't even know precisely the details of this one, but this is how here we're going to save these in these PEM files. And then we'll double check that that worked by printing it out. So again, we're going to save. We're going to come back here and run that again. Okay, cool. But let's see. Hold on. What did I do here? Oh, so right now we're just printing the type, right? So we've converted, what we did here is we converted those keys into the type PEM. And then here, excuse me, I got ahead of myself. Here is where we are saving them. We're actually writing them to the files. So we'll write them, save the strings, right? So we converted them to strings. We save them to PEM files. And then here we're going to print them out. Okay, so let's see what we got going on here. Ta-da! Okay, so this is what these type of keys would look like. And this is a very standard key format, right? Begin RSA private key. So this is what this RSA type key will look like. And then this is the public key generated from that. So we can go here and that, there we go. We created them. And again, we can do the same thing here. And we can have a look at them. All right, so we're doing pretty good so far. We have created these key pairs. We've converted them into this PEM format. We've saved them into files and we can have a look at them. All right, now let's convert these keys files back to RSA objects. Okay, so now we've got them saved as files. And again, this is just like stuff that might come in handy for you in the future as you're working with this tech, right? Here's how you generate it. Here's how you change formats. Here's how you save it. Okay, now you have this file saved somewhere. How do you then convert this back into something that we're then going to use, right? So then let's convert that back into RSA key objects. So now we're taking a file and converting it into an RSA key object. And then we're going to print that back out to make sure it's working. So now we're getting a lot of output every time we run this file, but it's good to take a look at it. So let's run it again. Here you can see all the previous stuff we've done. And then boom, here we're doing at the end. Yep, these are now RSA key objects, right? So we've successfully read those files and turned them into objects that we can now use. Okay, so now we get to the part where we actually use them. Now let's encrypt our message. Okay, so here we're saying what type of cipher, right, we want to use, what sort of encryption message or method we want to use. So we're going to use this method here. We're going to create a new instance of it, I believe is what's happening. And then here's the key that we're using. Go up and check. Yep. PU key. Right, there we go. Okay. And then here we create our ciphertext using the message, which again, we created all the way back up here. All right, so now we've told Python which keys we want to use. We've told it how we want to encrypt it, and we've given it the message to encrypt. So let's uncomment this, save the file. Now we should be able to encrypt that and then print it out to the screen so we can see the encrypted version of it. And boom, there we go. You can see to us that looks like gibberish, right? That is not human readable, nor is it really machine readable. It's just gibberish, right? It's not readable unless you have that decryption key. Okay. And here is where we do that. Once again, this is just giving you examples of how you can encrypt and decrypt in Python. Again, Bitcoin doesn't really do this, but working with this tech, you might want to do this in some cases. So we're going to decrypt, right? Here's the key that we're using to decrypt. Yep. So we encrypted with our pub key. We are decrypting with our private key. You can see here, private key that we're reading from that file. All right, and this is, the library we're using for it. We're using a new decrypt with this key. Then we're taking the message, right, which is our ciphertext, our encrypted text from up here that we just printed out, and we're running it through the decryption algorithm. Then we're going to drop it back onto the screen to print it back out in a terminal to make sure that it worked. So again, we're taking these files that we generated, we're reading them with Python, we're converting them into these objects. We are encrypting the data with this public key, then we're printing that out to the screen, then we're decrypting it with the private key, and then we're also printing that back out to the screen, or to terminal here. And there we go, it works. We once again have our message, I love cryptography. So here it is. We don't print it out up there. Okay, so here it is in its encrypted format. And here it is with its decrypted format. And then I think I just added this last line in here for fun. So if we come back there and do it again, boom, we are done. We successfully completed our exercise. And now is a great time to stop and go over questions on this. So Mike, if there's any questions, and we don't want to go too in depth on the specific math or functions here, but discuss more like how this stuff is used or where we might use it, etc. So Mike, do we have any questions?
Well, I'll give people a chance. I don't know if this falls into your category or not, but there is a bit of a discussion about the idea of public versus private keys and whether they're the same thing or different things, but I don't know if that's... Hello, public.
Yeah. So definitely different things, and this is one of the key takeaways of this unit, is that for a lot of Bitcoin's really built on this asymmetric encryption using these key pairs. Private keys is a bit of information, right? Sort of a string, or really, I guess, a number that you generate, hopefully randomly. And you have to keep that private. And then with that key, you can do all kinds of things like, sign data, etc. So yes, they're very different, and it's very important to get those differences. Pub keys are used to encrypt. Private keys can be used to decrypt. Private keys can be used to sign data, and then pub keys can be used to verify the signature on that data. So very, very cool stuff. And there's so much in Bitcoin, in the Bitcoin world, that depends upon that asymmetry. Asymmetry in cryptography using these keys, asymmetry in how different scripts are used. So yeah, very important to keep that in mind. There's definitely a big difference between public and private keys.
All right, well, thank you. I'm not seeing any other questions in the chat. Yeah, so if you guys have any questions, feel free to put them in the chat. If not, if you're watching this later, you can always put them in the comment section below, and we can get them to another time. I just want to, vamp for a little bit, give everyone a chance, but thank you, everyone, for joining us. Thank you, of course, Hannah, for taking us through all of this. And next week, we will be doing Unit 3, Unit 3 of this course at the same time. So get excited. The link to the course is in the description below. And again, thank you so much, Hannah.
Right.